In this session, let us try to model leakage. Actually, about leakage, there are two things which has to be discussed. In our first session, I told you that we are going to model leakage not because it is lossy, but it is except efficiency, remaining all performance characteristics are severely influenced by leakage. So, as leakage is influencing voltage regulation in case of transformer, what is voltage regulation? We will see later. Torque speed characteristics in induction motor, maybe voltage regulation in alternator, okay, maximum power handling capacity of synchronous machine. So point here is except efficiency, all other parameters or performance characteristics are influenced by leakage. So that's why we are going to model leakage. Actually this point I cannot prove now. Means let us go ahead, automatically you will understand. Next thing is leakage is linear. Why, you will come to know. At starting, as usual, we will go with a bit of small contradiction, and after that at the end you will get the clarity. For example, if I have transformer like this, okay, and this is going to be my primary and this is going to be my secondary. Okay, so let me consider transformer at no load only. Now let me connect one voltage source here, V1. Okay, at no load only, let us analyze the situation. Okay, now the moment V1 is there, V1, if it is 100 volts, automatically E1 should be 100 volts. Means automatically flux produced is going to be pi naught, kind of 100 flux lines with scaling factor we have been discussing. Okay, out of this pi naught, maybe some part of the component will go through secondary, some part of the component may not go through secondary. Like for example, if I have network, if I have very huge resistance here, maybe this is 1 ohm, maybe this, let us think of 1 kilo ohm, normal electrical network, and for example, if 5 amperes current is flowing through this, now how much is the current flowing through this? Current flowing through this is going to be 5 into other resistance 1000 divided by total resistance 1001. Okay, it's almost 5 amperes. It's because 1000 by 1001, so almost it's going to be unity, so almost it's going to 5 amperes. Now if I think of other current, component of current which is flowing through this, though this is having very high value of resistance, definitely some small portion of 5 amperes should flow through it or not. How much is the current flowing through it? 5 into other resistance 1 divided by total resistance 1001 amperes. It is not zero. So what is the conclusion from here? Though here I am having very huge resistance compared to here, definitely maximum portion of current will not flow, but at least small fraction of this particular 5 amperes has to flow through this, though it is having very high value of resistance. Similarly, now if I apply the same, out of this pi naught, reluctance of this is very less. Why? Relative permeability of the magnetic material is very high. So the moment relative permeability is high, reluctance is inversely proportional to relative permeability. So compulsorily reluctance is going to be less. So maximum portion of the flux will go through this. So let me think of this as mutual flux pi m. Now if you think of, definitely some portion of flux has to go through it. This is leakage flux. Why? Basically for pi naught, there are at least, like in a oversimplified way, at least there are two reluctances. What are those? Very less reluctance of this, like very less resistance. Very high reluctance of this, because it has to go through the non-magnetic material, like this. Now, though it is having very high resistance, can you stop the current? No. So, though it is having very high value of reluctance, can you stop the flux? No. Very small fraction of flux of total has to flow through leakage. For example, if I don't want to allow any current to flow through it, okay, so if I don't want to allow any current to flow through it, what I have to do? I have to open circuit. What is meant by open circuit? Open circuit means that we are going to provide electrical insulator here. Okay, so electrical insulator here, if I can provide electrical insulator here, then I can say total current whatever is entering 5 ampere should flow through it, because it's going to be having infinite value of resistance. For example, if at all, if I have magnetic insulator, if I fill that magnetic insulator here, then what will happen? For example, if you consider this leakage flux, the moment leakage flux come, it is not supposed to go through magnetic insulator, so it cannot flow through it. It is forced to flow through it. Like if I keep some electrical insulator here, all the current has to flow through this only. Similarly, if I have magnetic insulator here, whole flux will go through it. But do we have magnetic insulator? Means long back when I was discussing similarities between analogous electrical circuit for magnetic circuit and electrical circuit, and boundaries between electrical analogous magnetic circuit and electrical circuit. In the boundaries, I told you the second point that means we don't have any magnetic insulators which can stop flux flow through them practically. So the moment we don't have magnetic insulator, you cannot keep your magnetic insulator here because it's not available. So obviously means flux has to flow through it. So we don't have any magnetic insulator, so flux has to flow through it. Now if you think of this red line, is going to be leakage or not? Yes. What is the definition of leakage? Flux produced by one winding which is unable to reach the another winding is leakage. Okay, flux produced by one winding which is unable to reach the second winding is going to be leakage. Okay, now what is the conclusion here? Conclusion is very simple. Because of lack of magnetic insulator, leakage cannot be eliminated from any electrical machine. Okay, so again let me repeat, you have to make a note of it, keep 2 stars. Because of lack of magnetic insulator means 3 stars, because it's interview question. Okay, so because of lack of magnetic insulator, it's impossible for us to eliminate leakage from any machine. Okay, anyway, leakage has to be part of the machine. Now let us try to analyze leakage. Okay, so let us try to analyze leakage. Now if I analyze leakage, for example, if you think of mutual flux, my mutual flux is linear or non-linear? Okay, mutual flux is non-linear. Why that particular property is going to be non-linear? Because my mutual flux is going through magnetic material. But now if you think of my leakage flux is linear or non-linear? Maybe if around 50% of flux path is in magnetic metal, which is non-linear, and remaining 50% of flux path is in linear region, because non-magnetic material, because we have to fill this with transformer oil. Okay, so the moment it's transformer oil, because inside the transformer tank we are going to pour transformer oil, then we are going to keep the transformer structure. Okay, so here around 50% of flux path is going through non-magnetic electrical insulator, which is nothing but transformer oil, and 50% of flux path is going through magnetic material, which is non-linear. Now altogether means 50% of flux path is in non-linear region and 50% of flux path is in linear region. So altogether my leakage, is it non-linear or linear? Okay, now you may think that it is non-linear. Now let us analyze, because everything should be from analysis point of view. For example, let us consider previously we solved a problem, right? So in that problem we have taken 100 tons. Okay, so we have taken 100 tons, and if I inject 1 ampere with length of the flux path as 2000 centimeters, area of cross section of flux path as 25 centimeters square, relative permeability of the material as 2500, then we got operating flux of how much? 39.27, I think 39.27 microwebers of flux we got. Okay, so we calculated this. Now for example, in order to set up the same flux, okay, so in order to set up the same flux, if 50% of flux path is in non-magnetic material, so this red line is going to be non-magnetic material. red line is going to be non-magnetic material and black is going to be magnetic material. Now if I can analyze this, automatically analysis can be concluded for leakage, because in leakage around 50% of flux path is in magnetic and remaining 50% of flux path is non-magnetic. Here also around 50% of flux path is in magnetic and 50% of flux path is in non-magnetic. Again, the moment it's non-magnetic, we have to neglect fringing. Okay, so by neglecting fringing, let me continue the analysis. So let me write here fringing. Okay, so neglecting fringing. Okay, so after neglecting fringing, let me draw for this the model. The model is going to be, this is MMF and this is reluctance of core and this is reluctance of non-magnetic material. This is going to be the case. Okay, so reluctance of non-magnetic material, reluctance of magnetic material, reluctance of core magnetic, reluctance of non-magnetic, and then this operating flux already they have given 39.27 microamperes. Okay, now let me calculate reluctance of the core. Actually we need not calculate, because already previously whatever we discussed, those details are with us. Now reluctance of the core is going to be 1 by mu naught length of the core divided by area of cross section of the core. Okay, so this is going to be 1 by mu naught, relative permeability is 2500 into length of the core totally is going to be 2000 centimeters. So now it is going to be 1000 centimeters. So 1000 centimeters into 10 to the power of minus 2 divided by area of cross section of the core. They have been previously also 25 centimeters square. So 25 into 10 to the power of minus 4 meter square. And what is reluctance? Reluctance is going to be MMF by flux. Okay, Ni by Webers. So ampere turns per Weber. Dimension has to be written for ESC candidates. Okay, now if you observe this, okay, previously what was the reluctance of core we got? Means 1 by mu naught mu r is same, area of cross section of the core is same, but in our previous calculation of the problem it was 2000, but now it became 1000. Okay, so in our previous problem it was 2000 centimeters, now it became 1000. With 2000 I got 2.54 into 10 to the power of 6. So this is going to be 0.5 into 2.54 into 10 to the power of 6. So many ampere turns per Weber. Now let us calculate reluctance of non-magnetic material. Reluctance of non-magnetic material is going to be 1 by mu naught is same, relative permeability is 1, non-magnetic material. Now length of the flux path, okay, 50% of flux path is in magnetic, 50% of flux path is in non-magnetic. So this is going to be 1000 only into 10 to the power of minus 2 divided by area of cross section of the non-magnetic material after neglecting fringing is going to be 25 into 10 to the power of minus 4 only, because we neglected fringing. So after that what will happen? What is the difference between here and here? It is 1 by mu naught is same, remaining is same, it is 1 by 2500. So 1 by 1. So 2500 times of this. So this is going to be 2500 into 0.5 into 2.54 into 10 to the power of 6. So many ampere turns per Weber. Okay, or else I can say, means this is going to be 1250 into 2.54 into 10 to the power of 6. Okay, now let me take one example in our network theory. So if I take one example in network theory, for example, if I have two resistances of 0.5 ohm and 1250 ohm. Okay, now current is I, for example. I would like to calculate voltage. Now how much is voltage? For example, voltage equal to means 1250.5 into I. Okay, so 1250 ohms, 0.5 ohms. So can I approximate this to 1250 I? Okay, because this particular resistance is 2500 times more compared to here. Under that conditions, what I can do, I can neglect existence of this on paper in analysis, but existence of this particular 0.5 ohms will be there in the physical network, but on my paper I can short circuit this, because even if I short circuit this also, nothing is going to happen, because 1250.5. Okay, so 1250.5 I can be approximated as 1250 I. So the moment I approximate from here to here, what does it mean? My 0.5 ohms can be neglected. Now if I come back to here, okay, so how much is this? This is going to be 0.5 into 2.5 or something into 10 to the power of 6, and this is going to be 1250 into 2.54 into 10 to the power of 6. Okay, now 0.5 into something, 1250 into something, can I neglect this or not? Okay, so what does it mean? Means when, focus here, when around 50% of flux path is in non-magnetic material and 50% of flux path is in magnetic material. Under that conditions, 50% of flux path in magnetic material can be neglected in analysis, and flux can be assumed as flowing through non-magnetic material only by neglecting existence of flux path in magnetic material. Okay, because reluctance, if you see from reluctance point of view, we can conclude that. So what does it mean? I can assume this, for example, this is a network. I can assume this network as, see here, I can assume this network as, this is 100 turns, and this is going to be current, and this is going to be flux. Okay, so flux requirement is 39.27 microwebers. Okay, and what is the length of flux path? Total length of flux path is going to be, total is 2000, 50% can be neglected, so is going to be 1000 centimeters. Area of cross section of flux path equal to 25 centimeters square, and relative permeability of the total medium as 1. Okay, so what is the, because this particular conclusion will be used multiple times, including 3-phase transformers also. Okay, now keep a 2 stars in your class notes and make a note. What is that? When around 50% of flux path is in magnetic material and remaining 50% of flux path is in non-magnetic material, okay, magnetic, non-magnetic, under that conditions 50% of flux path in magnetic material can be neglected and flux can be assumed as flowing through non-magnetic material only. Now we got the conclusion. What is that? If you think of leakage flux, here, the moment you think of leakage flux, 50% of flux path is flowing through non-magnetic and 50% of flux path, around 50% of flux path is going through non-magnetic material. Under that conditions, flux path in magnetic material can be neglected and flux can be assumed as flowing through non-magnetic material only, making leakage linear property. Okay, so now I can say that leakage is linear because linearity is too much dominating compared to small non-linearity. So leakage can be assumed as flowing through non-magnetic electrical insulator only, making, how much will be the hysteresis loss for leakage? 0. How much is the eddy current loss for leakage? 0, because it is going through transformer oil. Now you have to keep 2 stars more, and you have to make a note. Okay, yes, around 50% of leakage flux path is in magnetic material and remaining 50% of flux path is in non-magnetic material. Okay, under that conditions, leakage flux can be assumed as flowing through non-magnetic material only. Okay, leakage flux can be assumed as flowing through non-magnetic material only, making leakage linear without having any hysteresis or eddy current losses. So leakage is going to be lossless quantity. So forget about everything. Now leakage is lossless. So the moment leakage is lossless, by which element or by which property of network theory we have to model leakage? Resistance? No. It is power absorbing element. Inductance, yes. Capacitance, yes. Okay, so by inductance or capacitance only we can model leakage. First point. And second point is basically inductance, capacitance. If you see, okay, so because of magnetic flux variation, if you get voltage, that will be inductance. Because of electrical flux variation, if you get current, that is capacitance. Okay, so in capacitance, what is capacitance? Capacitance is going to be IC equal to C dVc by dt. Okay, so because of electrical flux variation or because of voltage variation, if you get current, that should be modeled with capacitance. Now if you think of inductance, VL equal to L di by dt, or I can say d pi by dt, because the moment it is linear I can use either d pi by dt or di by dt because it is linear. I is directly proportional to pi. Now because of any current variation or because of any flux variation, because of any magnetic flux variation, if you get induced voltage, that should be modeled with inductance. Conclusion is very simple. So basically, first thing is we concluded from starting. If you observe, leakage, around 50% of flux path is of leakage in non-magnetic material. So as non-magnetic material is quite dominating, it should be linear. And leakage flux is flowing through non-magnetic electrical insulator, which is transformer oil. So electrical insulator, eddy current loss will not be there. So total core loss or total losses will not be there for leakage. So it's going to be lossless. The moment it's lossless, means with resistance we cannot model. So we have only inductance and capacitance. With capacitance we cannot model because of magnetic flux I am getting induced voltage. So it should be modeled with inductance only. Because of variation of electrical flux, if you get current, under that condition, it should be modeled with capacitance. Okay, so ultimately it should be modeled with inductance. Anyway, more depth. Okay, so means let me think of, already we know that our phasor diagram. So from phasor diagram, let us see, because with the phasor diagram, basically machine means analysis. Okay, so with analysis only, we will be able to get many things. Okay, with mathematics and all, machines cannot be understood. Okay, now let me start drawing the phasor diagram. Okay, now if I start the phasor diagram, first of all flux should be written. Okay, so let me think of this as flux, and now, okay, what is that flux? Is it mutual flux or leakage flux or total flux? Basically, if I see pi naught, okay, total flux is going to be mutual flux plus leakage flux, anyway phasor addition. Okay, now what about the magnitude of mutual flux should be more? Why? Reluctance is going to be less. So magnitude of mutual flux is very, very high compared to leakage flux. Why? Because reluctance of mutual flux path is very, very less compared to reluctance of leakage. Okay, now means what about my total induced voltage in primary E1? So my E1 magnitude should be equal to E1M plus E1L. Why? Because means my total induced voltage will be because of mutual flux also induced voltage will be there in primary, because of leakage flux also induced voltage will be there in primary. Now if you think of secondary induced voltage E2 will be decided by E2M only, because leakage flux is not meant to link both the windings, and we are thinking this at no load only. So let me analyze the situation at no load and let me extend the conclusions to loaded conditions. Okay, now means between mutual flux and leakage flux, which magnitude is more? Mutual flux. So let me consider mutual flux here. Okay, now if I think of mutual flux, okay, let me erase this. If I think of mutual flux, what about by E1M? For example, this is E1 induced voltage because of mutual flux, because pi M only I have taken. Now if I think of, this is going to be E2M is nothing but E2 only, because only mutual flux will come. Okay, now let us think of minus E1M. So minus E1M is going to be like this. Okay, so this is minus E1M. Okay, basically I2 I2 dash phasor diagram I am drawing. I2 I2 dash inline phasor diagram I am not drawing. Okay, at starting I introduced minus E1 equal to V1 phasor diagram and E1 equal to V1 phasor diagram also. After that I stopped, because once we enter into exact equivalent circuit and approximate equivalent circuit, we are going to analyze that. We are going to analyze both. Minus E1 equal to V1 phasor diagram kind of also will do, and E1 equal to kind of V1 phasor diagram also will do. Okay, now anyway, this is going to be the situation. And now if you think of no load current, so where my no load current will be, already we know that no load current should lead mutual flux. Why I am saying mutual flux? Because it is going to be non-linear. Okay, already we know that my mutual flux is non-linear, because which is going through magnetic material. Now where I have to draw pi L, because mutual flux is shown. Now I have to show leakage flux. What do we know from our previous discussion? Leakage flux is linear. Means that the moment leakage flux is linear, leakage flux should be directly proportional to current. Why it is linear? I is directly proportional to pi. So means I have to show leakage flux wherever current is there. So I01 is there. So let me think of, this is pi L, because leakage flux and current are in line. Now that for example, for that leakage flux, basically for this mutual flux I got induced voltage mutual. For this leakage flux I should get induced voltage in primary only, not in secondary. So 90 degrees to this, this is going to be E1L. Okay, because this is going to be E1L. Okay, with respect to mutual flux 90 degrees E1M, with respect to mutual flux 90 degrees E2M. So with respect to leakage flux 90 degrees E1L, and the magnitude of mutual flux is more, that's why E1M and E2M is more. The magnitude of leakage flux is less, that's why E1L magnitude is less. Okay, now minus E1M I have taken, so it should be minus E1L I have to take. So minus E1L is going to be like this. This is minus E1L. Okay, now if I write the equation, here, what is V1? Is nothing but magnitude of E1. Okay, V1 equal to magnitude of E1 is nothing but E1M plus E1L. Okay, so E1M plus E1L is going to be total E1. Now E1M is here. Okay, so if E1M is here, automatically E1L. Let me add E1L here. Okay, now E1M plus E1L is going to be primary induced voltage. So primary induced voltage is going to be, this is going to be total E1. Okay, now some people feel that means, for example, by which property we have to model this. Then automatically you will understand. If you think of voltage is here, current is here. With respect to voltage, current is lagging behind by voltage. So I should model this with inductance. Is it linear inductance or non-linear inductance? It's a linear inductance. Okay, linear inductance normally will show like this. Non-linear inductance. Okay, non-linear inductance, if at all, I have to model with two lines. If I show with two lines, means that it's iron core transformer. Iron core transformer in the sense non-linear will say. Okay, anyway, it should be modeled with linear inductor. Now some people feel that sir, if I consider E1L and I01, okay, if I consider E1L and I01, with respect to E1L, my I01 is leading by 90 degrees, because if I sit here and if everything is rotating in anti-clockwise direction, if I sit here, I have to look forward for current. So should I model with capacitance? No, because the moment I have taken minus E1M, automatically minus E1L only should be taken. Okay, if I take minus E1M plus E1L should not be taken. No, Okay, either minus E1 equal to V1 phasor diagram should be followed, or E1 equal to V1 phasor diagram will be followed. E1 equal to V1 phasor diagram we are about to draw in future once exact and approximate equivalent circuits are over. Anyway, we introduced that E1 equal to V1 phasor diagram previously. Okay, so the moment I considered minus E1m, automatically minus E1L only should be considered. Minus E1m minus E1L is going to be E1. Okay, now what about the no load component of power factor E1 to I01 is going to be theta naught, because total induced voltage is E1, current flowing through that E1 is going to be I01, so no load power factor is going to be theta naught. Okay, so conclusion is very simple. With linear inductor we have to show the leakage, or forget about all. Because of magnetic flux variation, some voltage is there, it should be modeled with inductance, that's it. Okay, now if you think of E1m plus E1L, E1 plus m plus E1L, is it representing KCL or KVL? KVL. Okay, so let us model that with KVL. Okay, if I model that with KVL, Kirchhoff's voltage law, we know that E1, okay, see, this is going to be, this is E1. E1 is having two components, that is E1L, E1M. Now the moment it is mutual, is it linear or non-linear? Non-linear. Similarly, in the secondary also, E2M will be there. E2M will be there. Okay. Of course, secondary leakage I will draw at later point of time. Okay. So this is going to the model at least for primary. Now try to do the same for under loaded conditions. For example, at starting what will happen under no load conditions? I01 is the current. Because of I01, my flux produced in primary is pi naught. Out of that pi naught, some component of flux will go, which is nothing but mutual 0. And some component of flux will come back like this. This is going to be leakage 0. Now because of this mutual flux, in secondary I am going to get induced voltage. Now in secondary, if I load secondary, okay, so if I load secondary, then what will happen? I2 is the amount of current. So in secondary total flux will come, that is pi 2. Okay, so in secondary, for example, if I think of in secondary, if some current is there, for example here, if I take some current here, I2 flowing through N2 will produce some MMF. Out of that, pi 2 will be produced. Out of that pi 2, some component of flux will go like this, some other component will become leakage. Okay, so this is going to be pi 2L, this is going to be pi 2M. Whenever a machine is loaded, automatically leakage will come. Okay, now if you see here, out of this pi 2, some component of flux will interact, that is going to be pi 2M. Some component of flux will come back here, this is going to be pi 2 leakage. Okay, now this is happening because of I2. Blue. Now the moment some I2 is flowing, which is giving pi 2 mem, it is trying to interact with mutual flux of the primary such that net flux is going to be varied. So in order to compensate that, my primary will take I2 dash current. I2 dash flowing through N1 will produce pi 2 dash. Out of that pi 2 dash again, pi 2 dash M will flow like this, and pi 2 dash L will flow like this. Okay, so my total leakage in primary is going to be at no load conditions plus loaded conditions. In secondary is going to be loaded conditions. Now my leakage flux will be decided by whom? For example, if I see this is my transformer. Okay, if I see this is my transformer. Okay, for example, if load current is there, which is flowing through N2, will create MMF across this I2 N2. Now because of that, flux will be produced. Okay, out of that leakage flux will go in this direction. For example, if load current is more, N2 is going to be anyway constant, because we are thinking as an operating engineer. If I2 is more, I2 N2 will be more. MMF across this will be more. Total flux produced by this will be more. If the total flux is more, leakage flux will be more. So I can say that leakage is directly proportional to current, load component of current. Load current. Now, logically speaking, this leakage flux in secondary will produce induced voltage in secondary, but will not produce induced voltage in primary, because leakage means the same. Leakage in the sense flux produced by one winding unable to reach the second winding is leakage. So, if I add this to here, okay, so here because of leakage or leakage flux, some induced voltage will be there in secondary. So this is going to represent this. So this is going to be E2L, and this is going to be total induced voltage in secondary. So E1L, E1M, E2M, E2L, E2. Now if you see, okay, in our first of the machine analysis, I told you that in the first case, ideal transformer analysis, and in the second case, modeling of practicalities. In the third case, finding parameter values of the equivalent circuit. Fourth case, analyzing the machine, practical machine. For example, means in the first case, ideal machine analysis. In ideal machine analysis, we got an equation. What was that equation? E1 by E2 equal to N1 by N2 equal to I2 by I2 dash. Okay, now this is meant for ideal machine. In the second case, we modeled practicalities, or we built the equivalent circuit. In the third case, we are going to find the parameter values by indirect loading test. How much is this value? Now, after that, in the last stage, I'll apply network theory from here to here. And from here to here, I have equation. From here to here, I'll apply network theory. From here to here, practical transformer has been analyzed, we can say. Okay. Anyway, coming to the point, we derived this equation. Okay. So we derived this equation for ideal machine. But now, means can I apply the same equation between E1 and E2? No, because in deriving this equation, we have clearly taken that leakage is not considered. Okay, now if you want to consider leakage, your equation should be changed. What is that equation? Between E1 and E1M and E2M only leakage is not there. So equation should be changed to E1M by E2M equal to N1 by N2 equal to I2 by I2 dash. Is going to be the under practical conditions we have to use. Okay, so there are two ways of analyzing the things. Directly, across E1M and E2M leakage is not there. So whatever may be the ideal equation, you please apply across these two terminals. Okay, or else you can do one thing that, use the same equation. For example, use this equation and keep the terminology like that. Or use this equation, change the terminology. In the sense, if I remove this as E1 and if I replace this as E1, if I remove this as E2, if I replace this as E2, same equation can be used. Both the analyses are right. In the sense, keep the terminology like this, change the equation, or keep the equation like that, change the terminology, both are right. Okay, all of our textbooks are using the same equation by changing the terminology. So we are also going to consider this only. So with this, I can say leakage is modeled. Now we may have to model resistance. Okay, we know that means if you think of copper wire, depending upon length of the copper wire, depending upon area of cross section of the copper wire, my copper wire will have resistance. Okay, of course skin effect will be there. I will explain about skin effect maybe in induction. Okay, but I will give you some conclusions in transformer, but I'll explain in induction, because in induction deep bar rotor, double cage rotor will be there. There if we can discuss that skin effect, it look good. Okay, so anyway, if you think of modeling resistance, Okay, so let me model, because resistance model is going to be very small thing. Okay, modeling of resistance, of winding resistance. Okay, if I try to model winding resistance, compulsorily one thing, whatever is happening in practical machine, the same thing has to be represented here. Whatever is happening in practical machine, same thing has to be represented here. Now in a practical machine, how much are the winding currents? For example, secondary winding. In secondary winding, I2 current will flow in practical transformer. So because of I2 current flowing through the winding, I2 square R2 will be the copper losses, if I think of R2 as the winding resistance of the secondary. Okay, similarly, if I think of primary winding resistance, leakage, non-linear, this is going to be secondary winding resistance, secondary leakage, this is going to be the model. Okay, in primary, whatever the current flow in primary winding, okay, whatever the current flow in primary winding, for example, this is going to be primary winding. Now if some current is flowing through the primary winding I1, because of magnitude of current I1, automatically you are going to have some copper losses. So means I have to keep some resistance value here on the on the paper, such that I1 should flow through R1. I1 square R1 will give you copper losses here, and I2 square R2 will give you the copper loss here. If secondary load current is increased, secondary copper loss should be increased. That's why I connected in series. Okay, now this is going to be X1 leakage of the primary, this is going to be X2 leakage of the secondary. Okay, now this is V1 primary injected voltage, and this is E1 primary induced voltage, we say. Okay, but ideally what is this? This is E1M, this is E1L. But it means we changed the terminology such that it became E1, and this became E2, and this became V2. So this is the series branch parameters, we see. Now we can conclude one thing, that series branch parameters, okay, because same current is flowing, so we call them as series branch. Now series branch parameters, basically R1 is showing electrical resistance of an electrical conductor for which Ohm's law is valid. So R1 is linear or not? Yes. X1 leakage is linear, we discussed a lot. So R2, X2 will be linear. So series branch parameters are linear. Okay, so once this is over, this is done. Now we are going to include what is shell type transformer, what is core type transformer, how leakage will vary. Why in core type transformer LV should be adjacent to the limb, and on top of that HV only should be there. In shell type transformer, why LV and HV should be pancaked or interleaved, we are going to discuss in the next session.